this morning is to quickly review the Euler Code that we talked about previously, and then we had structured the program in a certain way so that it would be easy to swap out, say, fourth order Runge Kutta for the Euler method without having to make big changes in our code. So to get started, let's have a look at the Euler Code again. I put some blank lines into this Euler Code in an effort to make things a little bit more clear. This first chunk is just bookkeeping, basically. We say what the name of the program is, we do the implicit none, and then we decided that we're going to store all of the t values and our approximate y values into two one-dimensional arrays, t and w. So we state that those are allocatable. We're also going to need a dt and f, someplace to store the actual solution, the beginning t value, the ending t value. T in, T out, Y in, and Y out are used in my Euler step. We will also be looking at the relative error, the worst of the relative errors, and the average of them. So the highlighted stuff, which is now no longer highlighted, is just setting up storage and declaring variables. The first thing that we're going to have to do is to find out what n is. This is the dimension of the problem. The 1, 2, 3 continue just gives me a place to loop to. I ask the user how many subintervals. I read n, and if there is an error of some kind, I loop back to the label 123 and then print how many subintervals appears on the screen again. The user is given an opportunity to try again. If the code gets to this point, then it has successfully read an integer in for n, but it's 0 or less, which is no good. So I decided that if that happened, we'll just halt program execution. I have to tell it what A, B, and I go on and calculate delta t here. I need to allocate memory for the t array and the w array. You'll recall that the index starts at 0 and goes up to n. As in the mathematics of the problem, t number I is I times delta t more than a, the initial time value. We have to state the value of the solution at the beginning, which we're going to store into w number 0. For our sample problem, that would be sine of 1.0d0. This code actually does all the work. I'm going to have I going from 0 to n minus 1, which means I plus 1 will go from 1 to n. Tn is the most recent time at which I know an estimate of the solution. T out is the time at which I want to know an estimate for the solution. My current estimate is w number I, and based on all of this information, call Euler step being sent Tn, T out, Yn, and producing Y out. Y out gets stored into w number I plus 1, and then we go around and do it again until we've computed all the quantities that we're interested in. In a very similar way, we're going to look at second order Taylor. I haven't bothered putting the extra spaces in, but nothing has changed in the main program whatsoever, except I've got a new call. Instead of calling Euler step, I call T2 step. The input and output parameters are exactly the same as before. After the call to T2 step, I store y out into w number I plus 1, exactly as before, and then we do the same reporting that we had done previously. Therefore, the only new features outside the main program will be, obviously, we have to write code to do this T2 step and any needed subsidiary problems. The same function as before, Euler step, which we are not using now. The subroutine T2 step accepts Tn, Tout, Yn, Yout, sends the answer back in Yout. This time I need to know two things instead of just one, though. I've written a routine to calculate the first and second derivative of y. From the differential equation, of course, the first derivative of y is just f at Tn, Yn. The second derivative we had to figure out by hand. Once we've got those two derivatives, though, if this were all that I were doing, I would be doing Euler's method. By adding this term in, we are including the second order derivative term in the Taylor series expansion, and then that's the end of our routine. The only remaining issue is to calculate the d1 and d2 using a routine called compute two derivatives. To reinforce the idea that what the calling program calls a variable and what the receiving program unit calls the variable have nothing to do with each other, in compute two derivatives, I'll call my input variables t and y. I'll send my answers back in first derivative and second derivative. First derivative and second derivative, when received by the TK2 step, are going to be called D1 and D2. It makes no difference. We did these derivatives in class, so I'll just write them down. Before, we gave Euler's method 500 subintervals, so let's do the same here. The average relative error is 2.9 times 10 to the minus 3, which is quite good. The worst relative error is 74%, which is pretty bad. But although that's a bad-looking number, we've seen visually most of the graph is in very close agreement with the exact solution. One can write T3 in the same way. In the main program, everything is exactly as it was previously, except instead of calling Euler's step or calling T2 step, we call T3 step. T3 step needs to know the first derivative, the second derivative, and the third derivative of y with respect to x. Pardon me, with respect to t, that is. If we were only doing that much, we would be doing Euler's method. if we were only doing that much, we would be doing second-order Taylor. The remaining new term is the third derivative times delta t cubed over 3 factorial being 6. Note the d0 as usual. I compute these derivatives in a subroutine that I'm calling compute 3 derivatives, which is very similar in spirit to compute 2 derivatives, except we're doing 3 instead of 2. We worked out these first, second, and third derivatives in class once again, so I won't bother doing that. Also, in the subroutine compute 3 derivatives, I'm calling the 2 values of the independent variables of f, t, and y, but I've gone back to calling the derivatives d1, d2, and d3. It makes no difference. Other than that, this is the same code for T2, which was the same code for Euler. And now we can see that the worst relative error is about 0.00893, while the average relative error is 3.74 times 10 to the minus 5 power. One can also code the fourth order Runge Kutta method. I'll skip over the second order one. I called it RK4.F90. Again, the main program is exactly the same as it has been previously, with the exception of this. I call RK4 step, but as before, I send it T in, T out, Y in, and Y out. This is my subroutine to carry out a step of fourth order Runge Kutta. Just as we mentioned in class, we have to calculate 4 of these K numbers, K1, K2, K3, and K4. If you'll consult your notes, you'll see that that's what we wrote down in the classroom. The Y out is going to be Y in plus 1/6 of the quantity K1 plus twice K2 plus twice K3 plus K4. And as you can see, there's been a considerable improvement in both the worst relative error and the average one. And lastly, I'd like to look at the extrapolated Euler method, which we had talked about previously. As usual, nothing different is in the main program, with one exception. As I go along, I'm going to check my extrapolation for early convergence. I'd like to know which outer iteration, which I value in the main program, such a thing might happen for. So I'm going to open myself up a file. I'm going to open Unit 25. The name of the file is goodbad. Status is replace so that I can write it if it already exists. In the main program, the only thing that goes on involving file 25 is it prints out the loop index of the main loop in the main program. Other than that, file 25 is not involved in anything else that goes on in the main program. We will have our extrapolated Euler step. we have our usual input-output, except now, of course, since I've opened file 25 in the main program, I should close it there. But other than that, there is no difference between this and the other programs, except the name of the step routine that we're going to use. This is the extrapolated Euler step. What we're going to do is we're going to say we want to move from T in to T out in terms of where our estimate is being evaluated at. What we'll do is we'll have an extrapolation table called T. In column 0 of T, we're going to put the Euler method solution based on one step starting at T in and going to T out. After that, we will cut the number of steps, we will double the number of steps, that is. We'll cut the delta T in half. We'll redo the calculation again, except the second time, I'll start at T in, end at T out, but I'll do it with 2 steps. The next time around, I'll use 4 steps, and so on and so forth. I'm allowing in my program for the biggest index to be 20, so I can imagine doubling the n about 20 times. We're going to go around in a loop, do I equal 1 to m. We're going to calculate an estimate of the solution at T out using extrapolation. So every time we're going to do this, every time we're going to get a new entry in column 0 of T, entry row number I to be exact. When we want to get an entry in row I column 0, here's how we'll do it. We'll initialize a variable z to be yn. This is going to be true for all of the estimates in column number 0. Then, for j equals 0 to n minus 1, we are going to do Euler's method, except we're going to do it n times. I had been experimenting with hard coding the function value n, but then I decided that's clunky and we don't want to do it. We find the time for the step number j within step number I from the main program. The function value will be the function evaluated at the time and the current estimate. We overwrite z with what it used to be plus delta t times f of t and y, loosely speaking. We store that number z into ti0, double n, cut delta t in half, go around and do it again. This is just Euler's method, except we are not storing these subproblems into arrays. We're just overwriting a variable. Then do k equal 1 to m. Bottom is 2 to the k minus 1. I goes from k to m, and this is our updating formula that we figured out for Richardson extrapolation. Now, generally speaking, it's a bad idea to test 2 floating point numbers for exact equality because of rounding error issues. But in this particular case, I'm going to do it because I want to check on something. The way we're doing our updating, the way we're getting our new column, is to take numbers out of a previous column and add this fraction divided by bottom. The numbers that we're really wanting, the TIK numbers by themselves, most likely are not 0. But that fraction that we're adding in. This fraction is going to be small if the method is working at all. So we're going to be running into the big number plus small number effect. I'm going to put in a little bit of extra code. In the loop that we've just finished, when we get to here, we've calculated the numbers tkk, tk plus 1k, and so on. Because of the big number plus small number effect, it's entirely possible that the numbers in column K that we have computed are exactly the same numbers as those in the corresponding positions of column K minus 1. If that's true, then to continue computing is silly because we're never going to get anything different. I'm going to declare a variable called badness. Badness being 0 means that those two columns are exactly the same and it's time to quit. So I'm going to look at row indexes k through m. I'm going to take the absolute value of the thing I just calculated in column k minus the corresponding number right next to it in column k minus 1. I'll add up all of these things. If even one of those numbers in column k differs from the one in column k minus 1, then badness will be positive. And as I say here, I really do mean to check floating point numbers for exact equality, because big number plus small number effect. So we're doing big number plus small number on purpose. So if badness is exactly equal to 0.0d0, then I'll set y out equal to the latest diagonal entry that I have computed. I'll print out to file number 25 the big plus small goodness happened at k equals, and then whatever the k is. Return sends program control back to wherever this routine was called from. End if, end do. Now, if the early goodness didn't get triggered, then I've computed all out to tm comma m as my last estimate, so I'll store that into y out as well. Giving it 500 intervals as usual, you'll notice that we don't instantly get our answers. It's having to think. If you think about it, this isn't all that surprising. 2 raised to the 20th power is a pretty big number. If it's having to go all the way out to that last row and column, this could take quite a while. Computers are fast, but they're not infinitely fast. And at the end, the worst relative error is 3 times 10 to the minus 10. The average relative error is 1.5 times 10 to the minus 12. So this extrapolated Euler method worked extremely well. Let's go look at good, bad. And you see, what I was hoping would happen has happened. These are not going all the way out to column k equal 20. I'm getting early goodness at stage 14, 13. I see some 10s and 11s. This seems to be pretty consistent all the way across the line. So by putting that check for early big plus small goodness business, we've considerably reduced the amount of computational effort. While I've been talking about this, a thought has occurred to me that would be, I suppose we'd call it, an extreme Euler extrapolation method. We may talk about that at some other date, but for now, I think this has gone on long enough. I hope everyone's having a good day. I'll see you again soon.